So let me make a remark, but maybe Shamik is missing. So recall that we had this while group action on the set pi int. So W acts on this, and there is this map which takes pi to pi 1. This is the weight lattice, and this was W equivariant, right? And so we had defined this S alpha tilde is an action S alpha tilde pi was defined for pi in pi int. So the definition of that was easy, and it was also easy to check that this was an involution. What was difficult was that this was they satisfied the braid relations. That was the hard part. Okay, but the purpose of this, for the sake of the while character formula, seems to be that the character is invariant, while group invariant, and for that purpose, as Vishwanath was making a comment yesterday, that maybe we don't need the fact that the braid relations are satisfied. Okay, and I agree with, after thinking about it, I agree with his comment. So so that simplifies the thing. So we don't really need the braid relations to say that that is invariant. What is important is that the W action here is lifted, which it is. That is easy to see from the very definition. Okay, what is easy to see is that this map is pi invariant, W invariant, W equivariant. And so that seems to be good enough to show that the character of B pi, which is W invariant, is W invariant, which was what we needed to as an ingredient in the proof of the while character formula. Okay, so it's just a comment. Now let's recall. Let me state the while character formula once again. So character formula. I say the while character formula, but we actually called it the path character formula. That's the correct way to do it. Path character formula. And what does it say? So I take pi in pi plus and put lambda is equal to pi of 1. Okay, maybe I'll write it here. Lambda is defined to be pi of 1. Then we have the B pi, then sigma W in W, sine of W, e to the W rho times the character of B pi is equal to sine of W lambda plus rho, where rho and B pi are as defined as usual. Okay, this is what we want to prove, we were proving, in the process of proving. A corollary of this is that it gives you the Weil character formula, remember, says that the character of V lambda is the right hand side divided by this. So the corollary, if you wish, is that this character of B pi is equal to, so the character of V lambda. And what is the proof of this? This is the Weil character formula. Right? Because once we prove this formula, once we have this proof, it shows that character of B pi is equal to the right hand side divided by this. But then by the Weil character formula, I know that the right hand side divided by this is the character of V lambda. This is clear? Okay. Now we also, corollary is also Lakshmibai Sheshadri character formula, which is saying character of V lambda is equal to summation over pi in Ls of lambda e to the pi of 1. And what is the proof of this? Yes? As of now, there is no relation. Okay? Yeah. Yeah. And as of now, there is no relation. Maybe there won't be any. Okay? So, that is a interesting question in the sense that we have a combinatorial object which we believe is a shadow of the actual objects. Okay, and why do we believe they are a shadow? Because they satisfy certain formal, because from the real objects we are producing certain combinatorial, producing some combinatorial objects, and these other objects. So what is so from V lambda is my real stuff. Character of V lambda is its combinatorial shadow. Okay, and this B pi is a combinatorial object which helps me calculate V lambda and has some, we believe, close relations to what is happening. Okay, but it's a real question as to, how close is it to V lambda? And in fact, you can generate mathematics out of this, in the sense that by asking, can I make it have some other property? Can I make it have some other property, etc.? For example, this here is saying that on B pi there is a Weil group action. Okay, that brings it closer to, that is one more thing that on which it has, which of course the character has it, right? But we are now lifting it to the level of slightly higher level of paths themselves. Okay, and so on. You can ask deeper questions. Maybe we will ask one such and try to answer it later towards the end of this week. Okay, maybe on Friday or Saturday. But that's a good question. So how close are these combinatorial objects to the actual objects of interest. Okay. So how close are the relations?
For the character it is obvious. Isn't the character will have this
No, I didn't. What's the question once again? No, I said the while group acts on the character. So the while group acts on the set of weights, and it's a simple thing to see that the while group the character is invariant of the is an invariant of the it's fixed by the while group. Okay, basically because you can restrict to SL2, and you know that a certain for SL2 you know that in an irreducible representation, if some weight occurs, its negative also occurs the same. Sorry, let me repeat it. So if it's an irreducible representation, then then either if m occurs, then minus m as a weight occurs, and with the same multiplicity. In fact, they are 1 if it's an irreducible representation. But in fact, in any representation, m, the weight m and the weight minus m have the same multiplicity for SL2. Okay, and using this, what you can do for a general, I'm just recalling now the proof for the Lie algebra case, general case. So you have these SL2 alphas, various SL2 alphas. You could take your representation, restrict it to SL2 alpha, and read this and apply this observation. Then you see that the character is invariant under S alpha. And since W is generated by S alpha, S beta, and so on, you get that it is invariant under all. It's a simple. That's the proof. That's how the proof goes. It's just the SL2 theory applied to the Lie, to a general Lie algebra. When you restrict to various SL2 alphas, you get this. And so it is easy to see that the character is while group invariant. Okay, so let's, maybe a picture will help. So if I so let's draw a picture. So you remember this picture of yes, this is the integrability condition in the infinite dimensional case. Yeah. Okay, let's draw this picture. Okay, do you remember the picture in the case of I think okay, since I've started it, let me do this. You remember once we calculated those 15-dimensional representation 3 epsilon 1 plus epsilon 2. Okay, so if you draw the picture for that, do you remember the picture for that? We can just generate it. Mrigendra, can you help me draw this, please? So this is my H beta. So beta is a root here. This is my beta. Alpha is the root here. So this is my H alpha. Oh, sorry. This is my H alpha. Okay, and Uh, in terms of yeah, you could write it like that, but since I prefer to also look at it in terms of the picture, so I've not left myself enough room. Okay, let's yeah, that I understand. Just help me complete the picture though. So this is two-dimensional, this is two-dimensional, this is two-dimensional, right? And so I am, however, okay. So this is yeah. So this from there, this, and from there, this one. So there. So, 3 epsilon 1 plus 2. So this is the one you calculated the other day, right? So it was 10 on the outside. Is this one more thing is missing maybe? Oh, was it 15, right? Was the dimension? 15. Okay. So that's the picture. Okay. So there you go. So the picture looks like this. Here, here. These are the single points. Okay. So this picture looks like this. And the point is, what is the while group? The while group is the group generated by these reflections, which means if I reflect this picture in this line, it is symmetric. So this is single, this is here, these two is here, this is here, and this point is here, and so on, right? And if I reflect it in this, the same thing holds. Okay, so yeah, because once it is true for H alpha and H beta, it will be true for H theta because it is in the group generated by H alpha and H beta. Correct. It's also true. It's also true for rotations by 120 degrees because that's also generated by this group. Okay, these two. So it is what I. So it is more or less easy to see that the character must be invariant under the while group. Okay, that says why the character must be a symmetric function. If you write it in terms of x1, x2, x3, for example, it must be a symmetric function. That is precisely the condition that it is invariant under the while group. Okay, so just to relate it with what Amri is doing, right? He is talking about symmetric polynomials S lambda. That is, when we say they are the character and it's a symmetric polynomial, that's precisely the condition that it is invariant under the while group, because the while group is just the symmetric group. Okay, and to say that there is an action on this is, or the while group on the set of paths is lifting that property of the character to the level of the paths. Okay? Okay. But as I was mentioning in the beginning, it does not seem to be important. It does not seem to be important that the braid relations hold. Okay? It does not seem to be important. What seems to be only important is that it lifts this. It lifts this and there is an action on the while group here. Okay? Anyway, the upshot, why I'm mentioning this here is the proof of the while character formula. I did the while group action on pi int, and it is done in the paper mainly because it is used in the while character formula, proof of the while character formula. but it seems to be not necessary. So that is something good, because it was a little complicated. So if we don't need to use it, that's a good thing. Okay. Okay. So so please tell me the proof of this corollary. What's the proof of this corollary? Right, B pi and Ls lambda are color directed graph isomorphic. Okay, so which means that they have the same, character. And that, so this implies by the elementary properties of characters, because so under this isomorphism, this pi goes to the straight line path, right? Okay, and then if I apply f alpha so many times, the same f alphas are applied here. And when I apply f alpha, I subtract so many alphas, right? If I apply f alpha once, then alpha is subtracted both sides. So it is this isomorphism, it weight preserving. In other words, the map. So right, there is this map here where this eta goes to eta 1, and here also eta goes to eta 1. Right?
The weight preserving will follow from this CDG isomorphism.
Yes. Yes. We will follow from the CDG isomorphism. Yes. So thus, character of okay.
Just to see if I understood it, like maybe the colored part is not necessary. This character graph isomorphism is enough to say multiplicity.
No, colored is important, because if I subtract alpha 1, I'm also subtracting alpha 1 there. So if I forget the color and just take the direction, I could have subtracted alpha 1 here, but alpha 2 there. That won't do it. Yeah. Right? Okay. So, and one of the things we will later do is also derive the Tableau character formula from this. Namely, that for example, for GLN or SLN, the lambda is given by a partition, and the corresponding semi-standard Young tableau with fillings by 1 through n of that shape. I can generate the character from that. That will also follow from the way we will do it in my part of the course will be by using this and saying that by a certain choice of pi, this B pi will turn out to be just Tableau. Okay? So later on we'll see Tableau character formula. So the idea will be for a certain choice of pi, B pi will be SSYT of lambda. Okay. Okay, let's now come back to the proof of this and what we were doing. Okay, so let me explain that. So the fact that this is invariant under the while group reduces, so proof of the path character formula. So we'll equate coefficients of E mu on both sides. Okay, may assume mu dominant because I can just multiply by W. So mu, e to the mu and e to the W mu have the same we'll have the, if I show that on both sides for e to the W mu it has the coefficients are the same, then for mu it is the same because I can apply W on both sides. Okay, so maybe I have not said that in a most transparent way, but this is anyway easy to see. We did this reduction yesterday. So let's assume mu is dominant, and for the case mu is equal to lambda plus rho. Okay, so here there was only one. Okay, so this is also done. Check that both sides the coefficient of e to the lambda plus rho was 1. Okay, the only way you can get e to the lambda plus rho here is take W is equal to 1. Okay, and you can get e to the lambda plus rho, the only way you can get is this W has to be 1 and this has to be the straight line path. There is no other way. Okay, this is also fairly easy to see from whatever we have done. You should do this as a homework if that is not clear. Okay, now let's come to the crux. And the crux of the proof is, suppose, okay, crux of the proof. So let me now summarize the situation once again. So we are taking mu to be dominant, but not equal to lambda plus rho. Okay, and checking coefficient of e to the mu on both sides. That's what we are doing, right? Okay. So if I look for mu on this side, remember lambda plus rho is a dominant, regular dominant weight. Okay. So when I act, so any element of, the only element of W that fixes it is identity itself. So the moment I apply something that is not identity, it will move. It will move to a different chamber. It has to move to a different chamber because the dominant while chamber is the, what is that? Fundamental domain. Is a fundamental domain. Okay. So it contains exactly one while conjugate of every, in the finite dimensional case at least, it carries exactly of every weight. Okay. Okay. In the Kac-Moody situation of the Tits cone, etc. But let's just think of the finite dimensional case. Okay. But so if it is going to, if some W is going to keep it in the dominant wave chamber, it will have to come back to itself. Okay. But there is, it's fixed, its stabilizer in the while group is just the identity. Okay, so it moves. So it's obvious that coefficient of e to the mu in RHS is 0, is clearly 0. Okay, and the content of the proof lies in showing that the coefficient of e to the mu on the LHS is 0. Is this clear? Okay. So we want to show coefficient of E mu in the LHS is 0. Okay. Now let us pay close attention to what is going on. Okay. So I now look at how all I can get E mu. Okay. How can I get it? So there is a W rho here, and there is a path here which ends at mu minus W rho for some W rho value. Okay, so that when I take the sum of those two, I get mu. In other words, I need to look at this set. So define, right? Sigma mu. This definition is motivated by looking at the contribution that I get to the coefficient e to the mu on the RHS, right? How can I get it? So there is a while group element and a path which together conspire to give me an E mu, right? So this is precisely the set of eta comma sigma. Let me write it like this, right? Eta is in B pi, sigma is in W, such that eta 1, the endpoint, right, plus sigma rho is mu. Right? So with this definition, the coefficient of e to the mu in LHS is what? For each of these I get a e to the mu, but with a sign, right? Okay. So what I have to show is sigma sine of this sigma, little sigma, of eta sigma in this sigma mu. There are too many sigmas, but oh, is this omega? Omega mu is equal to 0. Is this. Okay. So want to show, so the question is, how do I show this is equal to 0? This is the question, therefore, right? It is, this part is clear. So this part is the question. Now the proof is, the main part of the proof is this. Okay. So let's look at this more closely. So let me look at this picture. Okay. So it's very, I mean, at least I understand it much better if I look at this picture. So what's happening? Let's see. This is the dominant white chamber. Right? Lambda is somewhere. Okay. So let's say lambda is here. Right? And in fact, we are looking at lambda plus rho, etc. Everything. So if mu is a weight that occurs or endpoint, I am looking at mu plus some W rho. Okay. So mu is a dominant weight. Okay. Not equal to lambda plus rho. Okay. So I am writing it here. Okay. Now you see, rho in this case is what? Rho is this, right? Rho is this. This is omega 1, this is omega 2, and so so omega 1 plus omega 2 is this. That's one way of looking at it. Or if you want to look at half sum of the positive roots, the positive roots are this, this, and this. Okay? This is alpha, alpha plus beta, and beta. If I add them, these two together will give me another alpha plus beta. But then if I divide by 2, I just get back here. Right? So this is rho. You agree with that? Right? And what is W rho? W rho is just all the Weil conjugates of that. Means I apply the various reflections and get it. So if I apply this reflection, I go here, I just get the roots, in this case. And this. So these are the roots. Sorry, these are in this case, they are the conjugates of the, right? So what I'm looking at is here. So it looks like this picture here. So what I'm doing is, I am looking at paths eta that belong to B pi, and end at one of these points. Okay? If it ends at this point, then I know that minus rho gives me mu. Right? If it ends at this point, this is some Weil conjugate of rho. So this plus this gives me mu, etc. Okay? So what this is saying is something interesting. If I look at all the Weil conjugates that end here, all the Weil conjugates that end here, so there are some numbers here, right? The Weil conjugates, this is some number, this is some number, this is some number, this is some number, etc. Right? The number of paths ending at that point. Okay? So if I look at the number of eta such that eta 1 is one of these, okay, the contribution to whatever contribution is, that number multiplied by the sum. So this is associated to a certain rho. This, for example, is an identity. This is S alpha, this is S beta, and this is S alpha, S beta, this is S beta, S alpha. So these three are positive signs. Maybe these three are, because I'm adding rho. So sign, okay. So these, this is adding rho, these three are positive, these are negative. Okay, I hope you understand what you mean. So for this contribution, whatever number I see here, that is the number of paths ending at this, I must take that with sign 1. Whatever number of paths end here, I must take it with minus 1. And so on. If I take those numbers, multiply by these coefficients, plus or minus, and add, I get 0. That's the claim. Because it is eta 1 minus of this. So the one that corresponds to, see, here I have a plus. So the one that corresponds to the identity, when sigma is 1, I must end here, because that plus rho must give me mu. Okay? This means this minus W naught rho gives me mu. Correct? It's just a matter of seeing which one of these. Doesn't matter, you can change it because it all ends up to 0. So even if you do it the other way, you know, you multiply it by a negative sign, you will get 0. Right? Is this clear? And I want to point out the following. This is all the Weil character formula is saying. If you prove this statement, you have proved the Weil character formula. This, in essence, is the crux of the while character formula itself. Okay? So what we have to prove is that this property holds for the set of paths. Okay? I also want to point out that this is the kind of proof that we will do every time in this theory. So this is the kind of property in the proof that is crucial to the proof of the while character formula. So we show that this property holds for this combinatorial object. Okay? So similarly, for the de Mazur character formula, you will say that the paths there is a certain recursion, and you will say that the paths will follow that recursion. Okay? The de Mazur character formula. So you can replace de Mazur by any other xyz. Okay? To prove anything, what you will need is that there is a certain recursion, and that recursion is holds also for the model that you have. You understand what I'm saying? So anything that satisfies that recursion will satisfy that formula. Okay? So you can make your own combinatorial model. Maybe we are talking about paths or Tableau, but tomorrow you maybe want to make your own combinatorial model. And if you want to prove that calculates the character, the crucial thing will be to prove a property like this. So you will associate endpoints to your objects, and so there will be a certain type of shape lambda, meaning if suppose I want to attach a certain bunch of objects to this lambda, and then endpoints. So given a dominant mu, and looking at all these points, that is W minus mu minus the while conjugates of rho, and look at all the paths all the objects of your model that end at these points, that have this as endpoint, that must satisfy this recursion. If you can show this, then you know that the while character formula holds, and therefore that is the correct object, at least as far as the while character formula is concerned. Okay? So this is the crucial thing. Okay? And how will the proof go? The proof will go, as I said it yesterday, but it bears repetition, so I'll say it again. What you do is you match these up. So, but let me try to it's very tempting, at least for me, to try and prove this for the representation. Right? That is, what we are saying is, in terms of the representation, to prove the while character formula seems to be you have to do the following, precisely the following. You take the weight space multiplicities here at these points. Okay, there may be, some of them may be 0, some of them may be, depends on how mu is situated with respect to lambda. But anyway, so you have these weight multiplicities at these points, right? Okay. Is this clear? Mu is a weight, and I'm subtracting rho, and so there is a good chance. So these are some elements of the weight lattice. Okay, that's all we need. So each one of them has a certain weight multiplicity in V lambda, in the irreducible representation V lambda. Okay, I take that number and multiply that number by these signs. Either take it or it's negative. And when I add them up, I get 0. This is what you have to show. Okay? So, for example, if I try to do this in SL2, just to tell you, so lambda is somewhere here, lambda is very large, or lambda plus rho is lambda plus 1, mu is somewhere here, right? What is mu plus lambda, mu plus rho or mu minus rho? There are only two. So this comes with 1 and this comes with minus 1. If I add this multiplicity and this multiplicity, negative of this multiplicity, I get 0 because both of them are 1. Okay, that's a very trivial check, but it's worth checking. Okay. Let's do it for the adjoint representation of SL3. Okay, and I take mu to be the 0 weight. Okay, then precisely all these come with multiplicity 1. So all these are multiplicity 1. So there are 3 1s and 3 negative 1s. So that's 0. Okay, and so on. Okay, more generally, you know, since these are Weil conjugates, if I take the origin, these are Weil conjugates, they will all have the same multiplicity, and therefore half of them come with 1, half of them come with -1, and they add up to 0. Okay, I'm just doing these trivial cases just so that you get an idea of what we're doing. Okay, okay. So to prove this, what we do is, yes. No, this is, rho is very particular because rho came because of this formula. Rho is a very special weight. Rho is very special. Rho plays a very special role in this representation theory. Okay, rho is very special. Okay, it corresponds to that 1 plus the partition 1, you know, n minus 1, n minus 2, ... to 0. Okay. Okay. So what we do is the following. I'll try to separate this thing into two sets. Or actually the way the proof will work is we'll separate it first into several pieces, cut it into several pieces, and on each piece we'll do this, right? So what I'll do is I'll send, I will try to find some bijection between those within each piece, those with S alpha sigma, some of them will have S alpha sigma, and some of them will have sigma. That is, they will have opposite signs. Okay? So what I'll try to do is, so see, remember I have paths now, not just weights. So I have objects here that end here, that end here, that end here, that end here. Okay? I look at all these objects and try to associate, pair them up. Okay? I try to pair them up, but I try to pair them up in such a way that if a path here, it has a negative sign, I will pair it up with a path somewhere with a positive sign. Okay? And so then that gives me the cancellation. Correct? So this is what we want to do. So take a path, I repeat, take a path here. So this will be an isomorph, this will be on this set. I will put bijection from this to itself, involution in fact, but actually bijection is good enough. Okay? Involution in fact, but bijection, if suppose I have a bijection in such a way that the image of a path, image of a pair, eta sigma, the image eta prime sigma prime, say, they have opposite signs. Then I am done. Right? That's precisely what we'll do. Okay. So, given, fix, given fix eta sigma in, okay, which means it is some path. I have a path and it ends at one of the, it ends at one of these points, and after applying sigma I've gone here. Okay. So the claim is, here is something you have to prove. Claim there exists, okay, so let choose T naught maximal such that eta T naught plus sigma rho so in 0 1 such that this is regular, sorry, is dominant but not regular. Okay. Now, why should such a path exist? I gave this argument yesterday, but let me repeat. Okay. Okay. Now, where does this path start? So let us. So, in other words, so mu is here, right? Somewhere in the dominant chamber. There is no vertical thing. Sorry. Okay, so mu is somewhere here. Okay, and these are the sigma, the Weil conjugates of rho, right? And remember, this path will start because this starting point is 0. Okay, so this is mu. And so I have this, okay. So it starts here and ends up here, or it starts here and ends up here and so on. Correct? Okay. Now, if it starts at any one of, so why should such a point exist? That's the question. Okay. Now, if it starts here, or here, or here, or here, or here, that is, if it starts at any point other than this thing which is in the dominant Weil chamber, where does it end? It ends at, so this whole thing ends at mu. Sorry, eta ends at one of these points, but, oh sorry, I said it wrong. We start at one of these points and end here at mu. I am talking about this path shifted by sigma rho, right? So the path itself starts at 0 and ends at one of these conjugates, but once I shift it by the conjugate, it starts at one of the conjugates and ends up at ends up at mu. Correct? Okay. So if I start at one of these points and end up at mu, surely there is a point where it is dominant but not regular. Clear? Okay, because I have moved from a non-dominant chamber to a dominant chamber and I must cross a wall in between. Is this clear? Okay. So this argument, however, does not work if I happen to start from here and end up at mu. Okay? Okay. Suppose I started from here, ended up at mu, and I never crossed this wall or this wall, right? Suppose I started here, ended up at mu, and never crossed this or this. What does that mean? It means I am regular dominant throughout. I am regular dominant throughout. Okay? I must have started at rho. There is no choice. Because if I started at other points, I'm finished the argument. I must have started here, ended at mu, and entirely lived regular dominant, right? Because I'm assuming that this condition is violated. It's clearly dominant, but not regular. So it's entirely regular dominant, which means if I subtract rho, if I take a regular dominant thing and subtract rho, it is still dominant. So I'm entirely in the dominant Weil chamber. Okay? That means the path must be must end up at lambda, because it's the only path that lives entirely in the dominant wave chamber is the unique path that ends in lambda. Okay, so I must have started at rho and ended at lambda, which means my end point is lambda plus rho, but I have assumed mu is not equal to lambda plus rho. Okay, so that's the proof that this is such a thing exists. Okay. Okay, now what I do is I put an equivalence relation. So, yes. Regular dominant. And we subtract rho from that, it is still dominant.
Even if you consider half of rho.
Oh.
Actually, we are using the property that is minimal integrity property.
Yes.
Because that is integral value.
Correct. I should be more careful. Okay. So, see, okay, so I'll say it differently, okay. That's a good point. So, okay, one second. So, if it starts here, what is the condition? If it starts here and ends and is always in the dominant white chamber, okay. That's a good point you're making.
Mu is integral, have an integral property.
Yeah.
So mu of h alpha is integers.
Yeah.
And you are straight to rho. So then it will rho of h alpha is 1. So it is subtracted by just 1.
So maybe I'm using that as well. You're right. So maybe it also requires, sorry, but I appreciate your point. The argument I gave is not complete. Okay. So you should also use the minimal. Minimal is an integer. Minimum is an integer property. Okay. So let us. But that's a good. Thanks. I really appreciate that point. Okay. So the argument that I gave is. I'm happy you caught me there. So that's not good enough, as I agree. But we need to also probably use the minimal integrality property. So let us take that as a homework. Okay, homework. So starting at rho and ending at mu. If that path does not lie here, then it is actually goes into the only way it can if that path lies entirely in the dominant Y chamber, then it must be the shift of the straight line path. Okay, that's the claim. Okay, so complete the argument. Yeah, I agree. I was a little loose there. Okay, good. So let's do this. So I call introduce an equivalence relation. As follows: eta sigma is eta prime sigma prime if, so this is so if after choosing T naught as above for eta sigma, eta prime T naught, sorry, T plus sigma prime rho is equal to eta T plus sigma rho for all T bigger than or equal to T naught. Okay. So let us draw this picture here. So let's say my path started here, right? And that is after I'm shifting it by rho sigma. Okay, so this is the rho sigma I'm starting from. Sorry, sigma rho that I'm starting from, and the shifted path ends at mu. So it goes somewhere here. Maybe I'm just drawing something, right? And this is T naught, because that's the last time it is dominant but not regular. It's on the wall and come here, right? So some other path could follow the same, some other trajectory, but if after this point it hits this point, and it must coincide with this. For example, let us just draw some path. So maybe it is this, and at T naught it again comes here, and then beyond the T naught it is the same. Okay, so these two will be called related, and it's easy to see that this is an equivalence relation. Okay, so now the claim is that okay, sigma mu, okay, divide sigma mu into pieces depending on T naught. I hope you understand what that means. That is, with each path we have associated a T naught, right? And then those with the same T naught I consider, and those with some other T naught I consider, etc., etc. And within that piece, within those with the same T naught, I have further this equivalence relation. Okay, is this clear? So things may have the same T naught, but suppose this path, instead of going along this after this, if it went like this, it will have the same T naught but will not belong to the same equivalence class. Okay? Okay. So into pieces depending on T naught. Okay, so we concentrate on one piece. So I am only considering those paths. It doesn't matter which sigma rho they started from. They could have started at this point or this point, but now all of them have the same T naught. So this T naught is the same for all of them. I'm considering those, and now we concentrate on one piece, and then on each equivalence class within the piece. Okay. So now my involution that I wanted will live within this equivalence class within this piece. Okay, just on that portion of the whole set, it will work, but that's good enough. I can do it piece by piece, and then this sum is 0, and that next sum is 0, etc. Okay, so what is the equivalence relation? So remember, we are within the piece, so T naught is fixed, and within this equivalence class. Okay, so choose alpha, or choose once and for all. So I fix alpha simple such that my eta t naught plus sigma rho belongs to H alpha. Okay, now, so when that notation means I am choosing one eta rho is now eta sigma is a path, is a pair. Eta sigma is a pair which belongs to one of these equivalence classes. Okay, so I've fixed this. So now what I want to do is the following. I look at sigma, consider or put M, I define this. We stopped at this point yesterday. Sigma rho alpha check. Okay. Let me erase this. Okay, then I want to introduce my involution. Okay, so what is my involution? So introduce the following involution. On pairs belonging to the equivalence class of this eta t that we have fixed. Etas, sorry. So the involution is the following. So I take my eta prime sigma prime, okay, and so this is the clever part of the proof. This comes after, after searching for it, and then you find it. Okay, so eta, you map it to f alpha minus m eta S alpha sigma if m is less than or equal to 0, E alpha m eta S alpha sigma if m is bigger than 0. That's the definition. Right? Okay. Notice that I have S alpha sigma here. Right? So when I take the sign of that, what contributes is the sign. Right? So this eta prime, this is prime C. Okay? This is the fixed one fixed, and this is any element belonging to the same equivalence class, and this is the involution. Okay? So this the contribution of this is what? Is sign of sigma prime. what is the contribution of this? Minus of that. So they cancel out, right? That's the, so provide the moment, so all it remains to show is that this is an involution. Okay, if I show that, then of course I have to check that it makes sense, that that this actually belongs to the same equivalence class, etc. There is all those checking to be done, but once that is done, this is the proof is complete. Okay, so let's just check that. Okay. So what all do we need to check? So let's make a list of things to check. So this thing belongs to the same equivalence class, right? Okay, let's give this a, let's call this I, okay? So I of eta prime sigma prime is equivalent to, this is what we need to check. It's in the same equivalence class, right? And what else? I square is identity. Okay. Anything else to check? Yeah, I mean, maybe this is too strong. This is more than required, but enough to check. Let me just. Okay. If I check this, then we are okay. Right? You agree with this? I have not forgotten anything, right? Okay. Right. So that, okay. So in other words, so this is part of that, right? I mean, this is this belongs to, meaning. So let's make this, and in fact, is that correct? Right? No. So that part, okay. So what I'm doing is, sorry, I have fixed this equivalence. So what are we doing? Sigma, I'm taking this omega pi, right? Where is my omega pi? Here, this set. I've cut it up into various pieces, depending on T naught. So with each path, I associate a T naught. For each element of sigma pi, I associate a T naught, and depending on the T naught, I filter it. I partition it. Okay, and after I look at only one piece with a given T naught. Okay, and there I partition it according to the equivalence classes. But once this, yeah, and once I'm fixed that equivalence class, which means that, where did I erased it? That anything in that equivalence class has the same, after T naught they are the same, right? So all paths in that equivalence class look like, they may start at any of these points, but all of them reach here at T naught and follow the same path to mu. Okay? So this point is fixed. I fix a certain alpha. Because this point is dominant but not regular, there exists a certain alpha. Okay? This point could have been 0, in which case any alpha would work. Okay? But I fix a certain alpha, and that's all. if some other alpha works, fine. But once and for all, I fix for that. For that equivalence class, I have fixed an alpha once for all. I could have fixed an alpha for that equivalence class. Maybe beta also works. You could choose a beta, doesn't matter. Okay, is this clear? This kind of confusion appears in all such proofs. Okay, there are many proofs which have this template. You divide this into equivalence classes, and then introduce an involution on that equivalence class, and then want to check that. Where do you introduce this, right? And there will be some choices, and at what level you make the choice. This kind of confusion is there. So is this clear now? Okay. So let us check all this. Okay, it's a matter now. It's just a matter of checking. Okay, so let us check why this thing lives in the same. So eta prime sigma prime is also a path that it looks like this, right? Okay. So let us take this one, right? Meaning, I will assume that my eta prime sigma prime is this one and do the checking. For this, it is similar. Okay, will you believe that? That is, there is a case when m is bigger than or equal to 0, and there is a case when m is less. One of these two cases are similar. Just assume that we'll do one of them. Yes.
Actually, this mu must be regular dominant. In the extreme case when d0 is 1.
Mu could be.
If it is dominant but not regular, then there will be some reflection that will fix mu. So that reflection we can take.
That reflection you can take, yes.
Then we can simply apply it on any eta on sigma that will do the job.
Absolutely.
So in some sense, t0 is 1 is actually that case.
So what Venkatesh is saying is the following. See, mu is a dominant weight, that's all. All right. So for example, let us suppose mu were 0. Okay. Suppose mu were 0, then that would be this point would be mu itself. Right. The last point at which it is dominant but not regular would be mu itself. Right. And you could just apply. Then the proof is easy. He's saying just apply that reflection. Right. So you choose a reflection, choose an alpha such that alpha mu alpha check is 0, and it is easy to check that that this contribution is 0. That's what you're saying. Correct. Absolutely. Okay. So he's giving some explanation for the choice of this T0. Right. So it's so that may be a good point. So say if mu were itself non-regular, you would choose an alpha. The thing to look at is an alpha such that mu alpha check is 0. Okay. Now what is the next best? The last point at which you have such a choice, right? So that's that's what you meant, right? It's some kind of explanation for the proof. Yes. See, in the proof itself, you could just apply S alpha. and then it would be easier. That's, yeah, it's a, yeah. Yeah.
Just another one. This n is always like this strictly negative or strictly positive. Like 0 case for that.
Correct, correct. Why is that?
Because of this sigma rho alpha is more. Sigma rho is regular term. I mean, it's regular.
Yeah, correct.
Sigma rho alpha is never 0.
Yes, correct. So this is thank you. Thank you. Okay. So this is an observation. So this, observe. Because this is regular. Okay. So let us see what we need to do. So when let's look at this case. Right? What am I doing? I'm shifting. So first of all, let us check that this is actually a valid path. That I can. So check. So let's do the checking. So let's look at f alpha minus m eta prime. Why is it not equal to 0 first? Why doesn't it vanish? That's what I meant. Okay. So for that, let us just look at where does it end? So after I add it to sigma prime rho, it ends at mu, right? Okay. So right? So let us look at eta prime 1 alpha check. Let's compute that. Aha. So no, okay. So there is, I made a mistake in my definition. This should be for choose once and for all. So this should be sigma prime. So the m that I choose for this. Okay. So let's let's write m prime. M prime is rho prime. Okay. So I want to apply the involution on this. Okay. So I choose this, and this is m prime. Okay. So what is this? M alpha check, and this is minus, and what is this equal to? This is so this is bigger than or equal, so this is bigger than or equal to 0. Okay, and what is this? Minus right? So if I have a path with whose endpoint, okay, so if I draw the, let me keep this for a while, I'm not sure I will need it. Okay, so let's go here. So let us draw this picture of eta prime. Eta prime, this is H eta prime alpha. This is, I'm drawing the picture of this, right? So it starts at 0, right, and ends up at minus m prime, which is a positive integer, right? m prime here, this is m prime negative, so minus m prime is a positive integer. So any path which ends here, I am able to apply f minus m prime times f alpha. It could be bigger. It could be right. It's thank you. This is greater than or equal to minus m prime. Sorry. Thank you. So there is at least, so between 0 and this already there is more than m prime. So between the minimum and this there is, so the number of f alphas I can apply is definitely more than that. Okay? So this is okay, right? That it is non-zero. Okay? Now let us check why it belongs to sigma, this omega mu. Okay? So let us compute eta. So to say that it belongs to omega mu, so what we need to check. So this finishes the checking of this. Right? Now I am checking that f alpha minus m prime eta prime s alpha sigma prime belongs to this. I am checking this. Okay? Okay. Let's check this. So what do I have to show? That this this endpoint, right, is equal to plus this times rho is equal to mu. This is what I have to check. Okay, but what is the endpoint here? So it is eta prime of 1, and I have applied f alpha minus m prime times. So I must subtract these many alphas, correct? If I did it right. Okay? Okay. Plus s alpha sigma prime rho. So is equal to mu. This is what I am checking. Okay? But what is this? It is sigma prime rho plus sigma prime rho on alpha check times alpha. But sigma prime rho on alpha check is m prime. Did I? Minus. Where here it is m minus m prime? Here it is minus m. Okay, minus m prime alpha. But then this cancels with this, and this is rho mu mu, because the original eta prime sigma prime was in sigma. Okay. Okay, that belongs there. What else do I have to check? Okay, let's check the condition that beyond this point both are the same. Okay. Okay. Now what is it at this point? What is eta? What is, so let us check what is eta prime t naught. Let's check eta prime t naught. Okay. So what do I know? Eta prime t naught alpha check. Let us check this. So I am checking that because this is my value. I want to claim that at t naught it actually is already above the portion that is going to be changed, I think. That's what I want to claim. Okay? Or rather, sorry. What I mean is all the action of this, so when I apply this thing, all the action has appeared before, which means this portion gets shifted down by this minus m prime alpha, right? Okay. And then I'm adding this, which means I'm okay. That is the proof. In fact, this proof also gives you this proof. So what is this? Let's check this. But I know that right? Because at T naught it was the same as, I know this condition for eta sigma, but eta sigma and eta prime sigma prime are coincident for all points here. Okay. So what do I know? Eta prime T naught alpha check is therefore minus m prime. Correct? Okay. And after that, it lives in the
At T naught the value is minus m prime for each alpha.
yes. So this I've computed this. Sorry, is that clear? Yeah, at T naught. And also, let's see if I am saying this correct. It lies in the dominant wave chamber beyond, right? This part. So beyond that, it is bigger than or equal to this minus m prime. Okay. So in this picture, this is at T naught, it is minus m prime, and beyond it is above, meaning not below this one. Okay, correct? Because the rest of it is already dominant. So the difference I apply is, so between what happens between eta, so okay, I've added a sigma rho, but say take these two parts. So just to understand what happens to eta prime t beyond T naught, it is just, so suppose T is bigger than T naught, say it's here, the difference is this. When I take the difference, the shift by rho prime, sigma prime rho goes away. So the shift is just this much. So it is shifted by a positive bit. So this alpha, so what I'm saying is eta prime T alpha check is bigger than or equal to minus m prime for all t bigger than T naught. That's the crucial observation. So all the action, so when I apply this thing to eta prime, so I reflect some portion, right? I reflect, say, from here to here, but whatever portion I do, I must, all the illuminated portions live here within this, right? So this whole thing, so in other words, eta prime, so what's the relation between, so from there I conclude that eta prime t is exactly equal to eta t plus m prime alpha, right? For all t bigger than or equal to T naught. Okay. So when I apply this S alpha, if I add this shift, that is just sigma prime rho minus m prime alpha. So when I shift it, it will shift it by this. There is this minus p prime alpha comes in, and so thus eta prime t plus sigma prime rho is equal to eta t plus sigma rho for all t bigger than or equal to T naught. So this proves this. You agree? So finally, why is I square the identity? So I have to calculate this value for, that is easy to check because it is just I have applied S alpha of, so what is S alpha sigma prime. So So let's see. So to check this, right? So what is yes? So I have to calculate this m prime for the this one, correct? This is my now the image. I calculate the appropriate this number for this and apply this rule on that, right? So I have to calculate S alpha sigma prime rho alpha check. Okay? So what is this? It is minus of if I did that right, correct? Correct? Okay. So if I am here, then I do, so for example, if I've assumed that I'm in this case, right? So for this, the value turns out to be m prime was negative, so minus m prime turns out to be positive. And so how many I should apply E alpha m prime to this? But E alpha and F alpha are inverses of each other. So I get back. And so on S alpha, I make it S alpha of S alpha sigma prime, S alpha times S alpha sigma prime is sigma prime. Is this clear? So this is also checked. It's an easy check. Okay. So to conclude, so this kind of argument involving this very clever choice, etc., is where the all the action is happening, and but it is sort of natural to try and look for such a phenomenon, because that now is an established technique of proof. Okay. Okay. So what we will do tomorrow is prove the Littlewood-Richardson rule in terms of paths, and look at an example to begin with. Okay. Now that is very pleasant. Okay. Unlike these getting your hands dirty proofs, that is really pleasant. In fact, it just falls out. Okay. So it's a very pleasant proof. We've done all the hard work. We just reap the benefit of all that hard work, and I will illustrate by means of an example. Okay. And then we will see, we'll get into the proof of the isomorphism theorem. That's our plan. Okay, then we will really get technical. Okay. Yes.
So it seems like after the fact, it seems like what you have done is broken your path up into 3 parts. This overall path, one there is a segment from the origin to sigma rho. That's
Okay. No, but that's not part of the paths really, because path. Okay. Okay, but let's say.
Think of it separately. Look at that segment. Then a segment which starts at sigma rho till T naught. Then a segment which goes from that
T naught to mu. Okay.
the 3 bits.
Okay.
Now, what you've really done, the crux of the proof is you've taken the middle bit and you have applied S alpha to it.
Even the initial bit.
Correct. So separate, the initial bit separate.
The initial bit separately.
So you applied S alpha separately to the initial bit.
Yeah.
Different segment.
Yes.
Take the middle bit separately, applied S alpha to it.
Have I applied S alpha or a little less?
Because the middle bit means, it's concatenation. So you should
Oh, middle bit, yes, indeed. It is exactly m prime, yes. Appa, that's good. That's a good observation, yes. In fact, yeah, on the middle bit, I'm applying S alpha, yes.
then you're leaving the last bit as it is.
I'm leaving the last bit as it is.
So you apply this operation to this.
Yeah.
Ignore the first bit. Think of the middle bit, you add S alpha on it, leave the last bit as is. That's your operation. And begin the path from sigma rho, from S alpha sigma rho. Now the S alpha sigma rho, that bit and the middle bit together, they end at the point, they end at some point. But now since you have applied S alpha to both this segment and this segment, and since it lifts the weight, the new path will end at S alpha of that point, which is that point itself.
Yes. Correct.
That's the structure.
Yeah, very good. So let me just say that again because it's worth saying. So what Vishwanath is saying is, so, and it's worth analyzing these proofs. Okay, so you know, the more ways we have to look at this, it's really helpful. So the structure of the proof he's saying is, you look at this path. So there is, we have shifted the entire path by this sigma, let's consider this sigma prime rho, right? Here, sigma prime rho is this, and this T naught is the same for all the things in this equivalence class and this. So I've broken up, it's as if I've broken up this path. So imagine that I have added this. This is I have prefixed something, and then I have this path, and then I have this extra bit. Okay, so look at it in 3 bits. Okay, there is this initial bit, there is this middle bit, and this end bit. What we are doing is, of course, I am applying S alpha to this because I am moving from sigma prime to S alpha sigma prime. Okay, and on this, observe that this value here, it is exactly m minus m prime. So if I wanted to apply my S alpha tilde, my while group action on that, on this path, right? What would I do? I would apply F alpha. I would precisely do this. That's what I'm doing. Okay. And the observation is that, and this I'm keeping constant. Okay. And as he says, the fact that since I'm applying S alpha to this and S alpha tilde to this, and the S alpha tilde operation preserves the endpoint, it is to calculate this endpoint for this. So this calculation that we did can be thought of as, I just apply S alpha to, I take the endpoint of this original bit and apply S alpha, but then nothing happens to it because it's on H alpha. So that shows that it is the same, this calculation this calculation can be conceptualized that way. This is what he's saying. Absolutely. Thanks. Okay, we'll see tomorrow, meet tomorrow.